Let me explain the effect of using suction rolls in the feeding line of secondary battery electrodes. In the electrode process, nip rolls are commonly used for feeding the material. There are a steel roll, which is a driven shaft on the bottom, and a rubber roll on top, which helps feed the material stably. This rubber roll is referred to as a nip roll, and it is essential for tension control in roll-to-roll processing. Let's take a look at the environment in which nip rolls are used. In the coating process, to prevent the rubber rolls of the top out feed and back in feed from being contaminated by electrode powder, the electrode side is made to contact the driving roll, while the substrate side contacts the rubber roll. Initially, only the copper or aluminum substrate is fed, but as coating begins, the structure presses down on an electrode layer that becomes several times thicker. The nip roll contacts the electrode at the three coated sections labeled A, B, and C, while there is no contact with the uncoated areas. Due to the difference in coating thickness, the nip roll makes contact with the three coated areas, but in reality, only two of these areas effectively exert pressing force. This condition can lead to material breakage and wrinkles in the uncoated sections. To respond to variations in electrode thickness and wrinkling, operators often adjust the CPC, or coating pressure control, and frequently fine-tune the spacing of the nip roll from side to side. As a result, the operator's workload is increasing. Additionally, pressing inconsistencies arise due to variations in drying conditions and coating thickness across the electrode's width. Since the nip roll is made of rubber, it becomes contaminated if the electrode is undried or has uneven drying, leading to a deterioration in the nip roll's flatness. This causes an imbalance in the pressure applied to the electrode, creating gaps and resulting in slippage, which leads to speed hunting issues across the entire line. Such mismatches and contamination cause defects like pinholes and dents. Furthermore, regular cleaning and replacement to remove contaminants not only disrupt line operations, but also often lead to secondary damage to the nip roll during the cleaning process. Let's take a closer look at the coating methods. These methods have diversified, including full-width coating, stripe coating, full-width intermittent coating, and intermittent stripe coating. With intermittent coating, as the substrate and coating sections feed at regular intervals, the nip roll must continuously move up and down, which can lead to issues. In the case of stripe coating, the differences in coating thickness have the most significant impact, often causing wrinkles in the uncoated areas. To summarize the points discussed earlier, the nip roll presents challenges due to coating thickness variations, wrinkles in uncoated areas, and contamination, resulting in increased operator workload, quality issues, and cost concerns, requiring greater investment and varied approaches to maintain operational efficiency and quality standards. To address those issues, suction rolls were developed as an improvement solution. The suction roll is a method that wraps around the backside of the material and rotates to move it forward. Our company's developed suction roll is a new concept suction roll that uses a 1 mm thick SUS perforated plate on the surface in an integrated inner and outer tube design, unlike existing suction rolls that have a fixed inner tube and a rotating outer tube. By applying special treatment to the SUS plate, followed by chrome plating and polishing, we have created a product that prevents slippage and maintains high tension. Let's compare our suction roll with nip rolls and nickel mesh-type suction rolls. When using a nip roll, issues such as slippage, disconnection due to wear, mismatches, and tension hunting frequently occur. It leads to increased operator workload and safety risks due to thickness checks and adjustments. Additionally, roll contamination leads to surface defects on the electrode, while reprocessing the rolls and maintaining inventory contribute to increased costs. When using suction rolls with a mesh exterior, issues arise due to mesh clogging from semi-dried coatings or slurry, which prevents optimal performance. In the case of the anode, the mesh's lower friction coefficient can cause the electrode to slip, weakening the tension. Additionally, the nickel mesh is fragile, leading to damage from minor impacts. There are also limitations in production sizes since only specific mesh standards can be manufactured, resulting in low adaptability to varied specifications. This necessitates maintaining additional spare inventory, which further increases costs. In contrast, our suction roll features an integrated design without separate inner and outer tubes, allowing it to accommodate a wide range of customer-specified dimensions. The suction zones can be adjusted to fit the roll path, ensuring stable feeding with excellent tension and slip-free operation, thereby enhancing running quality. Defects such as tension hunting and wrinkling are minimized, as the electrode contact surface is made of SUS perforated mesh with a special coating that resists contamination. Specifically, contaminants are expelled externally through the perforated mesh and suction system. This design not only makes cleaning as easy as with a standard guide roll, but also minimizes surface damage, making it a highly durable, near-permanent product. To evaluate the tension of mesh-type and perforated-type suction rolls, we developed a specialized tension testing device and conducted a test. The test results are as follows. For the anode material, at an electrode width of 200 millimeters, the tension value of the perforated plate type that our company has developed was measured at 24 kilograms, which is 1 kilogram higher than the 23 kilograms of the mesh type. At 400 millimeters, the perforated plate showed a tension that was 15 kilograms higher than the mesh type. At 600 millimeters, its tension was 28 kilograms higher. This indicates that for the anode, as the electrode width increases, the tension value of the perforated plate type is significantly higher than that of the mesh type. For the cathode material, at an electrode width of 200 millimeters, the tension value of the perforated plate type was 1 kilogram higher than that of the mesh type. At 350 millimeters, the perforated plate showed a 2 kilogram higher tension. At 500 millimeters, its tension was 3 kilograms higher. This indicates that for the cathode, the perforated plate type achieves tension values equal to or exceeding those of the mesh type across various electrode widths. For reference, the suction roll imported from Japan, which features a structure with a fixed inner tube, rotating outer tube, and mesh covering, has been measured to have approximately 30% lower tension than our suction roll due to its lack of air tightness. In summary, the perforated plate type maintains high tension, demonstrating excellent performance in material feeding and tension cutting, making it highly effective even under high tension control conditions. Finally, regarding cost considerations, our suction roll features an integrated structure without separate inner and outer tubes, incorporating a rotating roll and a vacuum chamber. A bearing housing adjustment device is required to secure the chamber and adjust spacing. Unlike other companies, where customers must provide this component separately, we supply it as part of the package at no additional cost. This concludes the explanation of the reasons and benefits of using suction rolls in the electrode process. Thank you.